Okay, so uh, today we'll start a very crucial part of earthquake resistant design concepts. Uh, Maybe you have already heard about it earlier, may not have understood or appreciated its implications widely. Uh, but nevertheless, it assumes completely different dimension in the when it comes to earthquake resistant design, and particularly when we are emphasizing on preferred mode of damage in a structure. For an earthquake resistant design, a satisfactory design is one in which large amount of energy dissipation is possible by means of inelastic deformations, and those inelastic deformations have to occur in the regions which are assigned a priori. We know or we decide where the inelastic deformations have to take place and to what extent. And obviously, where it doesn't happen by chance, it has to be designed, the system has to be designed in such a way that our assumptions actually play out correctly, and that will happen. I mean, in order to achieve that, what we need to discuss, or the need is moment redistribution. Have you ever heard of this term, moment distribution, moment redistribution? Moment distribution, obviously, everybody must be aware of. I'm assuming use these days they do. They have not completely given up on manual calculations. Moment distribution and slope deflection, etc., are still being taught in the undergrad program. So, what is moment redistribution? Any ideas about it?
Sir, for example, in case of fixed beam, if one hinge form at one support, then the moment pattern, resistance by other section will change. That is reorient themselves.
Yes, because the moment capacities cannot keep on increasing, so the plastic hinge will extend its length, and the moment pattern will change. So that is, of course, moment uh, distribution in the section or in the span that changes. Now, there are very finer issues that need to be discussed, that you need to understand. Why did I say, I mean, it's very natural that if the when we allow hinges to form in the beams, then obviously there is going to be some changes in the moment uh, pattern in the along the span. So why is it such a big deal that we are that we are considering this? I'm calling it as a very crucial aspect of earthquake resistant design. Let us look at one more thing that I need to discuss. Is the simplified analysis. Just as for gravity load, we discussed about the equivalent subframe. So for lateral load analysis also similar concept exists. For example, a building, a frame, maybe oh, it's terrible. My hands are not drawing lines straight in this cold. Okay, let me. Okay, fine. And let's say these are the beam levels. So we can actually take out uh, and develop it as so. Just terrible. So again, we consider the mid height of the columns on either side of the one particular level of beams, and those are the points of contraflexure, as I had mentioned earlier. And then this is, let's say this is the jth level, and jth floor. So that's the equivalent lateral force that you find from the seismic analysis to be applied on at different levels. And obviously there will be shear forces. At these levels. So this is the equivalent substitute frame that you can use, and one round of moment distribution will allow you to calculate the bending moments for calculation in the for use in design. So obviously if you look at the gravity load moments would be, there would be very small, it starts from 0 and kind of this, and similarly something of this kind. And then the so these are the gravity load moments, something like this. So there will be negative moments on the column face, and then positive moments in the span, mid span, somewhere around mid span. Now because of the earthquake load, what happens is these moments are very, I mean, you can have very large moments. They can actually go, for beam moments, they can actually go like this. And column moments can be somewhat like this. Right? So the essential point that comes out of this is, most of the time you will find that exterior columns, outer columns, they are much heavily loaded. The demand is much heavier on the exterior columns. Interior joint columns, because of the counterbalancing action of the beams framing into interior columns, the net effect of the on the columns would be very small. So the additional axial force on the column because of the flexural action because of earthquake load, earthquake effects, is going to be very small. So not much needs to be done for the axial capacity of the interior columns. Most of the demand would be on the outermost columns. because there is nothing to adjust, nothing to compensate here. This particular negative moment that is coming from the uh, beams. Right? So high moment because of the on the is very large moment on the beam column face. Now, first thing, we need to obviously take care of the possible reversals in the direction, earthquake direction. So, we need to take into account the possibility of the moment pattern getting reversed because of the earthquake loading, and also we need to also take into account that what we will actually have is the combined effect of gravity load and the earthquake effects. So they do not, although in analysis you perform gravity load analysis separately and seismic analysis separately using different section properties, because for the earthquake analysis you do need to take into account the uh, possibility of not possibility, the reality of uh, cracking, extensive cracking in the section, and the cover is not being available. So you only take into account the confined core, and that reduces the stiffness, that reduces the uh, forces that will come on to the structure. Uh, Even the gravity load forces would be smaller when earthquake, when real design level earthquake actually uh, effects are to be accounted for. The structure comes into action along with earthquake load, and that's why whenever you have the earthquake load in figuring in the load combination, the partial load factor on the dead load and imposed load is actually reduced somewhat to account for the fact that the stiffness is reduced, and therefore the forces are going to be reduced on the section. But I would like to emphasize on the another aspect of this is, uh, keep always in mind our basic design philosophy. Uh, we are looking for strong columns and weak beams. Now, if you look at it, the beams, they have very large moment demand here, right? The negative moment on this beam column face is very, very high. Now, the positive moment on the other hand, if you look at a gravity load, there will be some amount of positive moment. The positive moment because of the seismic load is actually going to be not going to be contributing very significantly, because it will at the midspan it will be more or less a point of contraflexure. So very little contribution to positive moment coming in from the earthquake effect in the beam flexure. So the positive moment is actually very, very small compared to the negative moment. And there is going to be, I mean, if you have this high moment demand here, then obviously you cannot truncate the flexural reinforcement at this point. It has to go beyond. It has to go beyond the interior joint, and you cannot truncate that in interior joint, and that will be a complete mess. Beam column junction is very, very difficult, very, very congested with reinforcement, and you cannot really have that kind of anchorage and requirement, bend the pipe, bend the rods inside the beam column joint, beam column junction, to get the sufficient development length in order to develop the full bond. So it has to extend beyond the certain lengths until it achieves the bond strength. And in a way, that brings us, I mean, although we have to, our requirement is somewhere here, right? Our requirement is somewhere here, interior face, and the reinforcement continues through the joint. Flexural reinforcement will continue through the joint, and the chances are, and keep in mind, this has no effect on the because the moments are of opposing sign, so the column doesn't really have any significant flexural requirement here, interior column, because of this seismic action. But if I have to continue this flexural reinforcement above, extend this through the interior joint, then this section actually becomes over reinforced. I mean, it has an I would say not over reinforced, it has an, it develops over strength, right? Need to extend the flexural reinforcements for developing full bond. And this leads to overstrength. Another thing is, we also need some code provisions, very important. Another criteria is positive reinforcement at any section positive moment reinforcement should be at least 50% of negative moment reinforcement. Right, so this is of course always there, even in the dead load design. You provide this, you provide at any support where the negative moment is going, hugging moment or negative moment is going to be crucial. So even at those support locations, sections near the support, you would provide uh, positive moment capacities to be at least 50% of the negative moment capacities. So these two factors combined together, they give you, I mean, the actual moment capacity is actually much more in the beam because of the extending reinforcement bars. And if that happens, then the overstrength of beams may lead to development of plastic hinges in columns. Because see, by doing this, we are not adding anything to the capacities of the column. Column still remains the same. Whatever calculation we did for the strong column, weak beam, we added maybe 20% higher moment capacity to the column than the beams. But when we design for the beams, we design for the maximum negative moment, and then we also have this 50% uh, positive moment capacities at any section, and then of course the signs have to be reversed, so you need to work out that how it works in the combination with dead load, gravity load and the earthquake load. But you will find that first thing is it is the problems, first thing is very might be possible to have a very large difference in negative moments and positive moments. Right? So if there is very large difference in the negative moments and positive moments, first thing obviously it leads to very complex reinforcing detailing, and secondly it leads to uh, because of the need to develop the full bond, it needs to, if you provide for very large negative moment, then by force you are also required to provide at least 50% of that capacity as positive moment capacity, and that leads to overstrength in the beams, which is not accounted for in your design of the columns. So you need to, if you do this, if you I mean there is nothing to prevent you from designing for this. I mean it can be designed. The only thing that you need to do is uh, account for beam overstrength in the design of columns by suitably increasing column strengths. Right? So, and then all will be well, and we will still have strong column and weak beams. The only thing is you need to account for, you need to assess what is the overstrength of the beam by virtue of this uh, reinforcement extending to the full bond length, and what is the actual uh, section capacities at that level, and accordingly So it is not just the calculation that you arrive from this moment diagram. What you need to do is the second step. Uh, After you design the beams, you need to again calculate what is the moment capacities of the reinforcement that have actually been provided in the beam, and accordingly uh, make the column capacities about 20% higher than that. So once that is achieved, then of course we will still be adhering to strong column and weak beams concept, but the chances are it will lead to a very complex reinforcement detailing and very uneconomical design. Very high, large amount of steel would be used. So alternate is uh, we can choose to redistribute the elastic moments, accounting for taking cognizance of the fact that there is going to be plastic hinges developing in the when the design earthquake action is anticipated. Then uh, we can actually assign the moments here, what is the maximum moment that we need to design for, and try to make it the total positive moment, maximum positive moment in the section, in the span, equal to, more or less equal to the maximum negative moment in the span, approximately. We cannot obviously do that exactly equal, with the limitation that whatever is the elastic force level, whatever the moment distribution that we arrive from the elastic analysis, the redistributed moment should not be reduced to levels below 30% of the maximum elastic limit. So
Sir, please repeat that point what you told.
yes, I am writing it down. So moment redistribution to take into account the inelastic action during design earthquake, right? So try to so this will lead to economical design and simpler reinforcement detailing. Try to bring or maximum negative moments and or maximum is only going to be 1, and the maximum positive moment to near equal levels in a span. Right, so if there is a very large difference between the negative moment at the appearing at a beam column face and the positive moment in the somewhere in the midspan of the beam, then we need to look at a number which appears somewhere in the middle, so that that will be the target moment capacities for the negative as well as positive. But the implications are, if we reduce the moment capacities, if we reduce the moment capacity at this level, where you have a large moment as predicted from elastic analysis, you expect large moment here. But if my moment capacities, if I provide moment capacities only up to here, then obviously this is going to yield first. This will start yielding first, and then it will progress. Plastic hinges will keep on developing. So I need to provide special confining reinforcement, and the curvature ductilities, very high curvature ductilities will be required here, because the plastic hinge, the rotation sections will have to allow rotation in the section. So curvature, high curvature ductility is of course implied, and special ductile detailing is very, very crucial in those ranges, in those regions. But we also, and in order to ensure that it does not lead to a very large deformation, very large rotation, which will lead to other secondary effects, because all through we work with the proposition that the deformations are small, and secondary effects are not really, secondary effects including P delta effects are not really very strong to make it a matter of concern. But when the deformations begin to increase beyond a certain level, then obviously those assumptions are no longer valid, and things become more complicated. In order to avoid that, in order to avoid very large deformations and other secondary effects coming into play, we ensure that this reduction redistribution of moments should not be more than 30% of the level computed by an elastic analysis. Right. So, for example, at any level, if m I was the moment from elastic analysis, then I cannot go sorry, 70% mi elastic is, this is the minimum moment capacity at a section after redistribution. And of course, redistribution, moment redistribution only changes the increments of positive and negative moment capacities. Right? Such that total moment at a floor level is same as that arrived at computed from elastic analysis. Right, so while individual section capacities, we can play with the individual section capacities, we can reduce the negative moment capacity here, and correspondingly we can increase the positive moment capacities here in a way that the maximum positive and maximum negative moment capacities are somewhat close to each other, so that the reinforcement detailing becomes simpler and easier to implement. And then once that happens, then there is really, if it is uniform, then there is really no need to truncate or reinforcement, flexural reinforcement in the interior joints, and they can the reinforcement bars can continue over the span, and that will take care of the other moments as well. So, but this increment, the decrease here, increase here, they should be complementary in nature, such that the total moment of the at a particular story level, total moment is not altered. So this is something that is very, very crucial, and we need to account for, diligently adhere to this redistribution principle, and simple equilibrium always has to be maintained. These column shears have to be consistent with the moment, total moment that is coming up, and that equilibrium, of course, will have to be in the, even in the redistributed moment at different sections, joints. You will still have to ensure that the equilibrium is maintained, equilibrium is satisfied. And when you take into account all these, and then go with the design, you will achieve obviously reduced moment capacities, reduced reinforcement details requirement, because of the moment capacities are reduced, and positive moment would you would anyway have reinforcement running in, so that will account for the capacities to take care of the positive moments as well. And the it will also lead to this redistribution also eliminates flexural, providing flexural reinforcements because to maintain the strong column and weak beam concept, you need to enforce that also in critical internal columns. Which carry very little axial force due to earthquake effects. Right? So there is actually no requirement for the interior columns for carrying additional axial force. So the reinforcement details, etc., are very, very nominal. But in order to maintain that strong column, you would need that columns have to be stronger than the beams. And if you do not account for this redistribution of moments and reduce the moments on the beam column interface, then the columns have to be provided with these additional flexural reinforcements, which are actually not required. Had it not been for these additional moments coming from the beam, high moments coming from the beam framing into the column, uh, and the beams at two ends of the column might be of a different span, and therefore, and that is why I'm not saying here that the columns, interior columns, will not carry any axial force. There might be little axial force because of the difference in the moments of the beam which are framing into the column from different ends, but difference in the moments will lead to very high negative moment, will lead to unnecessarily increased demand of flexural reinforcement in columns to increase the moment capacity of the columns, whereas axial capacities do not really require that much reinforcement. Right? So that again adds to the economy of the design. So if you can redistribute the moments, then the demand on the column also reduces, and it becomes much economical to go with the design of the entire system. Right? So is this clear? Any questions? We will take up the individual design philosophy of the individual structural members from the next week onwards. I hope I can be more regular from next week onwards. So tomorrow, of course, is a holiday. So if you are free, we can have class tomorrow.
Yes, sir.
Yes, sir.
Yes, sir, no issues. Yeah.
Okay, so we can engage class tomorrow. Great. So we will meet tomorrow again at 10, and we will start with the design of individual members, starting with flexural design of beams and followed by shear design of beams.
Sir, any update regarding exam?
Come again? What about exams?
Any update मिला है क्या मतलब
Oh,
एग्जाम
update.
होने वाले?
It's going to be online only. The exams will be done in online mode. The modalities are yet to be worked out. I mean, there is no I mean, that we have already decided that there is no plan to call you back on the campus anytime soon. Now, how this will happen?
Sir, any specific dates are there, like
Oh, that
given in the
that's
previous schedule, the 20th of Jan? Is it?
yeah, that calendar still holds. 20th Jan is the date, still the target date. But it might have to be staggered because there are lots of issues. Earlier, it was probably that 1 week was set aside, 20th Jan to 27th Jan. Uh, depending on the number of courses and number of uh, examinations for different students. I mean, you of course have only 5 courses to 5 exams to write, but others might have more number of courses, and depending on the electives that they register for undergraduate students. So the exams window might be extended a little bit because we need to allow for make a provision for charging of the communication devices. Right? Your laptop needs to be after 2 hours examination. I mean, your laptop batteries need to be charged again. And okay, Rais, you are from Kashmir.
No, sir.
You are not from Kashmir. So who is from Kashmir? There were a couple of students from Kashmir, I guess.
Yes, sir. I think two of them are there from Kashmir. I don't
So
remember
what
the
is the
name.
network condition there? Because the requirement is, at least that is what being discussed about the proctoring. All of you have to enable the video camera all through the examination.
Yes, sir, not too good, as he was not quite regular in the classes. He also mentioned that
Mm-hmm.
the networks are there, sir.
Okay.
So
Okay,
he
fine.
used to skip maybe like 1 week, 2 weeks. Sometime he used to skip. That
Mm.
was
But has it not been restored now? Uh, high bandwidth, I mean, 3G, 4G connection in Kashmir? You don't have any idea. Okay, fine.
no, sir.
Okay.
No, sir. Not 4G connections.
Okay. Okay, let us, we'll figure out something. Okay, so I'll stop here. We will meet again tomorrow at 10. Yep. Thank you.
Thank you, sir.